All right, so now we're going to talk about another method for testing critical points to determine whether they're a local minimum or maximum. And that's the second derivative test. So as the name implies, we're going to use the second derivative to determine whether a critical point is a local maximum or minimum. And by using the second derivative, we're looking at the concavity of the function. So if the second derivative at the point P, or critical point, is greater than 0, that means it's concave up. And so this is a little illustration of a concave up function. And so you can see that if it's concave up, then at our critical point, then it has to be a local minimum. And if the second derivative at that point is less than 0, meaning it's negative, right? Meaning it's concave down, then that critical point is a local maximum. Okay, and so it's sort of illustrated here. Now, if the critical point, if we evaluate the critical point at the second derivative, it's 0, then it really doesn't tell us anything. Okay, so that's all we have to do. We have to take the critical point and evaluate the second derivative at that critical point to determine whether the function is concave up or concave down, and then that's going to tell us whether we have a local minimum or a local maximum, or we don't know, right, if we get a 0. So let's take a look at this same function. This is the same function that we used in example 2 and example 3, I believe. X cubed minus 9x squared minus 48x plus 52. And we want to use the second derivative test to confirm that we have a local maximum at x equals -2 and a local minimum at x equals -8. All right, we've really already confirmed it with the first derivative test. Now we're just going to apply the second derivative test. So in order to apply the second derivative test, we have to have the second derivative, right? So we found in example 1 that the first derivative is 3x squared minus 18x minus 48. Okay, now I'm going to take the polynomial form of it rather than the factored form, just because it's easier to take the second derivative. We have to take another derivative. We're taking the derivative of the derivative, right? That's the second derivative. So if I take the second derivative, it just becomes 6x minus 18. Okay, and now all I need to do is test the critical points. So if I look at f double prime, so the second derivative of -2, then just plug it in the value, plug the value into the function. We get 6 times -2 minus 18. Now, obviously, without doing any calculations, you can tell that that's going to be negative. Now, I could calculate it out, and I can see that it's minus 30, but it really doesn't matter what the value is. It just matters whether it's positive or negative. And in this case, it's negative, so that tells us that the function is concave down. Concave down at that point, which tells us that the function has a local maximum at that point, right? Because it's concave down. So sometimes I just like to draw a little just to remind myself, okay, concave down looks like that, and so that has to be a local maximum. And if I evaluate the second derivative at the other point, which is 8, I got 6 times 8 minus 18, which is actually a positive 30. And that's telling me that the function is concave up at that point, right? So concave up, it looks like a U. And so you can see that the value, the critical point at x equals 8 is a local minimum, all right? So we can conclude that by the second derivative test, f of x has a local maximum at x equals -2 and a local minimum at x equals 8. All right. So I'll meet you in the next video.